Well, the example above showed that really all we have to do, if we're given a function of two variables describing a surface, if we subtract z from both sides, then we get a function of three variables. And if we find the partial derivative of f with respect to x at the point given, and the partial with respect to y at the point given, and the partial with respect to z, but if you subtract a z from both sides, you just always get -1 from that. And then use the point x minus x0, y minus y0, z minus z0, use the point in that fashion. That will give us a tangent plane. So let's do maybe a nice easy one here and sketch. And sketch is something I could hardly ever do in person, but I can make the software show a pretty plausible sketch. So find and sketch the equation of the tangent plane to the graph of the function at the point. Okay, here's our function. Here's our z equals f of x, y. It's 1 minus a 10th x squared plus 4y. And one way it looks like it'll be parabolas, the other way it looks like it'll be a straight line. So interesting. And the point is given as 1, 1, 1/2. X is 1, y is 1, z is a half. So expressing this surface as a level surface from a function of three variables gives us this equation. And the partial of this with respect to x, you can see if you multiply it by 2, we get -2/10 x, so -1/5 x. Partial with respect to y is just -2/5 because the y has vanished, and the partial with respect to z, as always, is -1. That's always when we use this technique. And we want to evaluate those partials at the point x is a half, x is 1, y is 1, z is a half. So put in 1 for x, we get -1/5 times x minus 1, the 1 from here, minus 2/5, the partial with respect to y, times y minus 1, and then minus 1 times z minus a half, this a half right here. And that can be pretty easily simplified. I won't bore you with the details, but you could add z to both sides and then collect up the like terms on the left. You get -1/5 x and minus 2/5 y. That's pretty easy to see. I'm going to change this, when I multiply it by 1, I'm going to change it to +2/10, and this -2/5 times this -1 makes it a +4/10, so we got 2/10 plus 4/10 plus 1/2, which would give us 5/10, so we got 11/10 altogether. So there is our tangent plane. So here they're both defined for my software, and I should be able to see the picture. And here is the picture of this situation where we've got a nice tangent plane at the point where x is 1, y is 1, and z is a half. It might be hard to determine the half here, but I think if you could see a little bit of the z-axis, half would be right about here. So it is that point right about there on that surface. I could probably show you the surface without the tangent plane. Oh, let me see how I could do that. Oh, I'd have to get this out of the way, and then, oh no, that didn't help at all. Sorry. I thought maybe if I got that out of the way it would help, but what it did, it went by the tangent plane I found to the other graph. So never mind me saying that I could do that. Oh, and I'll tell you how I could get rid of the tangent plane. Just go here and delete that graph, and now we'll see it without the tangent plane. See that surface, and at the point x is 1, y is 1, and z is a half. You can see a little better there. And here it is with the tangent plane. I'm drawing the function f and the function g at the same time, and there's the tangent plane. And isn't life wonderful?